Okay, good afternoon. Let me start my talk. Of course, let me just reintroduce myself. My name is Qingyun Duan from GSIS, College of Global Change and Earth System Science. Today, my talk is about quantification of parametric uncertainty of large complex geophysical models. So just I think probably, the talk today may have some repetition, from the morning or other talks in the following days. But this is my version, okay? You'll hear other versions of this uncertainty quantification talk. Okay, the motivation is simulation-based science provide a powerful complement to experimental science. We talk about like subground, underground nuclear explosion. Nowadays, it start or not for us to have actual explosion. We have to use computer model to study this kind of processes. Of course, climate model. When we talk about projecting climate change 100 years from now, there's no way we can do experiment to see what's going to happen. And there are a lot of other kind of geophysical phenomena. We have to use computer model to gain understanding. So there's a lot of uncertainty associated with geophysical models. So you have input uncertainty, and you have state uncertainty. And also you have model parameter uncertainty. And actually, this is what we are going to talk about today. And there are other uncertainty, like the model structural uncertainty and the model output uncertainty. Just give you a few examples. Probably you already know, many of you. This is an example that came out of, I think Charles probably were involved sometime in the past, in the 90s. This Purpose project, a program for intercomparison of net-surface model. And so this is the partition of evapotranspiration and the runoff. And because it's constrained by the precipitation, so it fall on this line. But you see all those different things actually mean different models. So we have the same reality, but different models have different realities. Okay, so there's a lot of, that tells us there's a lot of uncertainty in the model. And so this is Purpose 2A, 2B, and 2C, and 2D. And all the models, we talk about 10 years apart, those four phases. And the uncertainty has always been there. And there is something I fear, even though there's a lot of work has been done in terms of trying to create the best model possible, but people haven't paying attention to the uncertainty. And so this is another example. The modeling community, the climate modeling community have seen. This work is, this part is from Thorsten, more recent. This here actually, you talk about two ensembles. One ensemble is the CMIP3, the night shaded kind of. This, each of those scale represent a different model of the global temperature. Okay, I'm talking about global temperature over the 150-year period. And the dark line are the observation, and then the red line is the ensemble mean. You can see there's a lot of model, between model uncertainty. The model, you talk about 150-year average. There is a 3-degree difference. And this morning I mentioned to Charles, you talk about, some model have no CIs, other model has a lot of CIs. So the way people trying to address this actually right now use a fixed CIs. That means the ice doesn't change with the temperature, it's prescribed month by month. And so this also, gave us pause on how we interpret the IPCC output. So how do we reduce the uncertainty? Okay, there's many ways. Okay, one way is to enhance the model physics representations, and this tend to be efforts of a lot of people, and so we want to have better models and CMIP and all those things. Tell us right now, there are more and more models, and my I heard that next CMIP6, there are 8 models from China, and so it's going to be more than 60 models in the CMIP6. And I'm not saying you shouldn't do it, but that's a lot of people have been doing that to create their own model. And there are other ways to improve model physical representation. You can use higher space-time resolution. You can use better numerical schemes. And another way, actually, in terms of trying to improve is using enhancing the representation of external forcing and the boundary conditions. Okay, so this means we use better observational system and then better data assimilation methods. And there's another way we are going to talk about today is to enhance the estimation of model parameters. And we're talking about tuning model parameters so the model simulation fits the observation. So that's the 3 horsemen. We are talking about. There's this modeler. Okay, a lot of modelers here, and then the data assimilator, and the calibrator. Okay, so it's like the Terminator and the calibrator. Okay. So why this parameter estimation has not really, I think, especially in this community, the climate modeling community, has not received as much attention as the other things. Actually, a lot of people working on the model itself, a lot of people working on data assimilation. I think the reason is because the parameter uncertainty, you have this high dimensionality problem. First, in the parameter space, you talk about tens or hundreds of model parameters, and then this high dimensionality of model outputs. Because in those atmospheric model, we are interested in many different processes. Now we talk about the precipitation, surface temperature, wind, pressure, humidity, and etc. So you cannot just tune to one observation. You have to tune to many different observations. Makes things very difficult. And it's very difficult to understand the parameter uncertainty. Usually, I think the model are not created by you, it's created by some other people, and you probably even don't know what those parameters are supposed to mean sometimes. So that's a difficulty, and then this is a major constraint. It's too expensive to run the model. Climate model is in a different category. You talk about sometimes days to just make one simulation. And there's a lot of other problems I don't want to read through. You have nonlinearity, data scarcity, and then this model are just not created. It's created from ideal condition, and so you have this unknown. This phrase coined by Donald Rumsfeld when he was talking about the war in Iraq, why U.S. suffer those different losses in there. So we have to quantify all those parameters. And here, I want to present a way we can address the uncertainty. Basically, you want to first define the problem. You want to choose the right model to help you to understand the process. And so you have to characterize a priori the uncertainty and then the next thing you do actually is to do a screening. You reduce the complexity of the problem, and then there's another technique. It's called surrogate model. So you construct a surrogate model. Once the surrogate model is constructed, then you don't have to run your dynamic model anymore. So that's the thing, once you have that, and then you can do other kind of analysis. So that's the idea. And I only have 1 hour to talk about. Actually, I can spend a week to talk about the stuff we have been doing. And there is a software platform. I forgot to put there is the address. Okay, there is a web address. It's called uq-pyl.com or .net. I cannot remember. But anyway, people interested, contact me, and you can go and download. And so this software package has a graphic user interface. It has all kinds of different functions, and it has those DOEs. You have those uncertainty analysis, sensitivity analysis, And it's like a playground, for all kinds of different methods. Okay, it has. We trying to put all the popular ones in there, and so if you play with this, you are able to to play with different algorithms. For each of those components, we have many different choices you can play with, and so it's suitable for parametric uncertainty analysis of any computer simulation model. As long as you have a executable code, we don't need the source code, and you have the control file which allow you to run the model, and then you have the output of your interest and the corresponding observation. Then you can do anything. Any model can work with this framework. So it can be a space shuttle problem, can be a deep ocean drilling problem, can be a climate model problem. So, yeah.
On the previous slide, you talk of screening analysis, that's reducing the complexity of
the
problem.
Yes.
Now, I'm wondering if by reducing the complexity, you don't introduce uncertainty. Given that, I feel that to model a situation, you must make it as close to reality as possible. But given that reality is most at times complex, now while doing some screening analysis to reduce that complexity, do you not introduce? Good
question. We're going to talk about that. Because the reason we want to reduce we only focus on the sensitive parameters. Okay, some of the parameters, if you tune it, doesn't make a difference to your model simulation. So I'm going to touch on that. Actually, I want to go faster. I know, I don't have too much time. But anyway, so I want to just give you a little sense of those different methodology is all about. And I don't think I have time to go to the detail in a lot of those different algorithms. But your question is going to be answered. So the design of the experiment, what this is supposed to do? Okay, design of the experiment is a statistical methodology for systematically investigating systems output-input relationship in order to achieve one of those goals. Okay, so identify the most important design variables. So this is the screening. Okay, we're talking about optimize the process or the product, and then also achieve robust performance. And for people, there's many books on design of experiment, and so here we're trying to use this to achieve this. The importance of identify the important parameters. There are many ways, many different approaches. Okay, so one approach we call a deterministic design, which the design, what is the design? Design is you do experiment. Like in our case, is like we trying to play with different parameters. The deterministic design, that means you put point in space which is not random. Okay, so the 4 factorial design, the fractional factorial design, those different designs are all deterministic. And then there's a random design. I think probably a lot of people heard of Monte Carlo. It's the typical random design. Latin hypercube can be random, and the symmetric Latin hypercube, etc. And there is those so-called quasi-random design. It looks random, but it's not actually random. It's generated by some kind of algorithm. So you can have some kind of uniformity property in parameter space. So this is just some examples. Okay, so the Monte Carlo, this is just draw from a distribution, and then you have this called factorial design. Okay, so factorial, you can see like it's 10 by 10, so it's all fixed in space, and then this is an example of quasi Monte Carlo. Like this is like we also sometimes call it LP tau, and in the LP tau category, you have different sequence. You have Sobel sequence, you have Halton sequence. And all those are created out of some kind of equation. Okay, so they put point in space, and they have uniformity kind of property. And for people doing numerical, like those kind of numerical schemes, and they're trying to partition the domain, and the methods design actually also can be a design for screening. And so just, 4 factorial, you can see that it's, if you partition into 5 levels, okay, then this is 2 variables. Okay, S is the number of variables, and M is the kind of levels you work with. So this will grow exponentially with the dimensionality. So if you have a 10-dimensional problem, 10 to the 5 power, that's a lot of about 5 variable to the 10 level. It's a lot of numbers. Okay, I confused myself right now. Anyway, okay, so this design works for when the number of variables are very, very low. You talk about 2-dimensional, 3-dimensional problem, and maybe you can deal with that. And then Latin-Happy cube, you can see Latin-Happy cube has this property. If you project all those samples, each partition only has one point. And if you go this direction or go this direction, like it's 5. Okay, so they use fewer samples in space, trying to capture, trying to explore the space, and we can have multiple replications. Okay. Sometimes it's also called fractional design. But if you have like 5 replications, then it became a 4. If it's orthogonal, kind of 5 replication, then you became a 4 factorial. And so the reason we use this, those kind of design can help us to understand the stochastic property in the domain. And for instance, we have using Monte Carlo trying to understand the average of this domain. Okay, so this is the histogram, and so like right now, suppose like right now we want to understand the mean of that field. Okay, we can do like 100 Monte Carlo. Each time we sample 100 times, and this is the mean. Okay, you can see there's a lot of uncertainty in the mean when you use Monte Carlo, and you can reduce the uncertainty by increasing each experiment. You have 1,000 instead of 100, then you can get a lateral range for the mean. But if you try use this is again is the 100 replication of 1,000, and if you using the Latin hypercube, actually Latin hypercube can give you a much tighter kind of mean. So that means using the Latin hypercube, you have much more confident estimates of the mean. If you use just a pure Monte Carlo, then the mean actually sometimes you have a lot more uncertainty. Okay, so just tells you, okay, the number of samples help you to reduce the uncertainty, but just a little bit. But if you use some kind of design which has uniformity property, you can get a much more confident estimate. So you can have less uncertainty. So there are different ways of doing parameter screening. This is just design. Okay, design is just a fourth step for doing the parameter screening. Parameter screening, based on various sensitivity metrics, is designed to separate important model parameters from unimportant ones. Okay, so this answers your question: why we want to use the screening. The screening, we choose the one which, if you assign different values, will generate big difference in terms of model output. And so when we use the screening, okay, when the number of parameters is very, very large. For instance, we talk about tens or hundreds of parameters. We cannot optimize that many. Okay, you have to reduce it, and the model is computationally expensive. So that's another thing. Because if you just couldn't afford to run too many experiments, and the thing about the screening, screening usually, they use limited number of experiments that give you qualitative kind of answer. So there is a Morris method. I think probably, I don't know if it's already talked about, but I'm sure it's going to talk about in the future. This is the one popular screening method people use. The way it works is like this. You change parameters one at a time. Okay, so this is one pass. Okay, then you can do it multiple times. Okay, you can do it here, and then you can do it here and here. Okay, so it's change one parameter at a time. And so how do you compute the sensitivity index? Okay, so this is the way to do it. Okay, so for instance, you started, this is the original point you started with. Okay, then you perturb one dimension, okay, by data x, and then you compute this thing here. Okay, the zj, So this is a gradient. Okay, this is like a gradient, and so you put it in here. Okay, you do it for all the for the entire path. Okay, and so you get, once you compute the path, you get this D1 to Dm. M is the dimensionality of your problem, and then so this is just one path. You got this. Okay, you do multiple paths. In the previous slide, it was 3 paths. So R, the big R equal to 3. Okay, so you have 3 of those kind of vectors. Okay, so what do? You compute the average of the 3. Okay, so you got this. So each parameters, you got something like this. Okay, this is a measure of your sensitivity. Why? Because the gradient, when you go from one point to another point, you have a big gradient. What that's supposed to mean? It means the model, when you change the parameters, it had a big influence on your model output. Okay, so this is a measure of the sensitivity. Okay, there's another measure as the standard deviation of this thing here. Okay, so if we plot it on this thing here, okay, so this is the mean is on this line. Okay, this is the standard deviation. So so each dot represents one parameter. Okay, so this is sensitive. This is not sensitive. Okay, so that's how Moore's one at a time or Moat algorithm works. Okay, and so there are other methods. Okay, there is a method. It's called tree-based method. It's I don't know if I have time, but just give you a rough idea of how this thing works. Okay, so if I have a 2-dimensional problem, okay, suppose this is a dimension, this is another dimension. Okay, so tree regression trying to use those kind of step kind of function to approximate the surface. Okay, and so how do you do it? You partition your domain into those kind of regions. Okay, so how do you do it? You look at sometimes the terminology is called impurity. Okay, so you look at this dimension, see how much variability in this dimension is. If it's very, very variable, then you partition in that direction first. Okay, and then just move to here. Okay, suppose like right now, you have the samples. Okay, the design, and then you compute the variance on this axis, the compute the variance on this axis. So if the variance on this axis is bigger than this, then you put a partition in there in that direction. Okay, and then in those partitions, then you do it again. Okay, you say compute the variance here and the variance on this direction, and then say the variance on this direction is bigger, and so you put all other partition in here. Okay, so you do it. Eventually, say okay. Each of those boxes right now, the impurity is within the tolerance. So there's not much variability in that box anymore. Then we stop. Okay, at the end of this process, then you count the number of partitions in each direction. If the partitions is more, then it means it's more sensitive. The partition is less, then it means it's not as sensitive. So that's the idea of this tree-based method. There are a number of screening methods work on this kind of principle. Is like the regression, the use regression, trying to capture using the parameters as predictor to capture the response surface. Okay, so if I include that variable as a predictor, it makes a difference in my feeding quality. That means that parameter is very important. If I remove that parameter, doesn't make any difference in terms of feeding, then that parameter is not important. So this is a category of so-called screening method based on regression. So basically trying to tell you how important it is in the regression process. If it is important, then it's an important parameter. If it's not, then you can throw it away. So I don't have time to go through all those different methods, but there are many, many different methods. If you want to play with it, the UQ PyL, the UQ Python laboratory, you can play with a number of those. Okay, so I welcome you to contact me to use that software. And so this is so-called, the screening is qualitative kind of approach. There is also quantitative approach. Quantitative approach trying to not just understand the importance of parameters, but also understand the contribution of the importance. That means relative importance. Okay, so the variance decomposition, of course, like when you look at that variable, how much that variable contribute to the total variance, okay? And my case, main effect actually is a variation of this variance decomposition. And there is this Fourier amplitude sensitivity test is trying to look at those kind of spectral domain and in terms of the different parameter from the spectral domain. And the Sotteri actually is a variation of this Sobos methods. And so this is the whole rationale behind this variance approach. Suppose you have a function, it's a k-dimensional function, and if you break down the equation in this kind of form, okay, so you have this only associated with xi only, and then you have this xi and xj only, and then eventually you have everything. So if you can break down this thing in this form, and then you can compute the variance for each of those terms, okay? And then the total variance is the sum of all those different variances, okay? The Sobel approach actually have a shortcut to estimate the total variance and then the fourth order variance. The way they do it, so this is just some terminology, okay? So like right now, the sensitivity index, so the main effect is the fourth order effect, the variance associated with the parameter only, okay, divided by the total variance. So this is the fourth order effect. Then this is the so-called the second order effect, is the variance associated with xi and xj divided by the total variance. Okay, so this is the second order effect. And then the total variance is all the terms which involving this index, okay. So in the Sobel approach, they make use of this property, okay. So the total variance is the variance of the expected conditional expectance of given xi, okay, plus the expectation of the variance. So this is if you want to go through the derivation, and this is a universal property for any of those kind of random variable you work with, okay. So right now, if you can compute this, and then this actually is the this divided by this is the variance, the fourth order variance of I. So that means if you can compute this, and then you can get the fourth order variance, okay. Just explain how this thing works. Okay, suppose like right now, so this is the kind of experiment. You can have this kind of experiment given x equal to 0 to 0.1 and all the way to 1, and then you do those many different experiments. And so what this term is, because this is the expected value given x equal to 0 to 0.1, so this is the expected value, okay. And then, so this term actually is the variance of this line here we are talking about, okay, the variance of this straight line. And then this term actually is the average of this variance, okay. So that means if you go back to here, this term and this term are all can be illustrated by this figure here, okay. And so once you have that, you can do, because this property also holds for any kind of conditional conditions, okay. So you have these two as conditions, you can do the same thing, okay. So you can compute the fourth order and the second order using those property here, okay. So I don't have time to give you some illustration, but I have some illustration. I deleted because of the time limitation, and so the advantage of those quantitative approach is not just give you the importance, but also give you the relative importance. That means this one contribute to the total variance 30%, that one 20%, that one 5%, and etc. So you get the quantitative sense. And now let's talk about surrogate model. Okay, surrogate model. Let me see. Okay, I have to go fast. Surrogate model is a this is the real world. Okay, we're talking about. Okay, so you have a spinning real world. Okay, and so you have this is suppose you look at this as a system. You have stimulus, of course, the sun, the solar radiation, or the the gravity. So the Earth spinning around the sun, and then of course you can use the dynamic model to represent this thing. Okay. And so when you do that, it's based on physical processes and very computationally extensive. And what is a surrogate model? Surrogate model, actually, we don't look at the spinning Earth. We look at the response surface. Okay, that means your arrow, the feeding of the arrow function. And so, oops, I'm sorry. So we not look at the dynamic process anymore. We just look at subgiving the dynamic processes. We figure out the arrow. The arrow, each of these thing is you can use a different experiment to approximate this arrow. Okay, arrow function. So once this thing is constructed, then the optimal here is the optimal of this dynamic system. So that's the idea. Okay. So surrogate model, this actually came from, I think, the paper from Roggio. They use the illustration to talk about, like right now, so this is the dynamic model response surface. Okay, then you want to use a surrogate. So this is the statistical model of this. Okay, and so there are many different names for surrogate model. You have response surface method, you have emulator, you have meta model, and etc. And so the basic ingredient is that you have to use a sample, use a design to to generate this kind of input-output pairs, and then you have to have some kind of feeding methods. Okay, so just surrogate model is very, very useful when we look at complicated models. Okay, so the idea is using sampling approach and assumption of the function f to construct this kind of mapping, approximate mapping. Okay, so usually the surrogate model is done after screening. Okay, you don't work with 40 or 50 parameters. You cut down from 40 to 50 to maybe, in my experience, I think actually is around 10, at most 15. You don't go more than that. Okay, so you cannot work with too many parameters. Okay, and also you have some kind of assumption about the response surface being smooth. Okay, if it's not smooth, it's very, very rough, and then the response surface method or the surrogate modeling approach may not work as well. So this is the illustration. This is from O'Hagan. So like suppose like right now, you have a one-dimensional problem. You sample 2 points in space. Okay, so any point passing through those 2 points can be regarded as a surrogate model of this true response surface. Okay, so right now, if you only have 2 points, then you have a lot of uncertainty. Here, you're pretty sure, but in here you actually have a lot of uncertainty. So to reduce uncertainty, you can put more points in there. Okay, suppose you put another point, and then you can reduce the uncertainty. Okay, and if you put more points, and then basically in between, you are pretty much sure. Okay, for this one-dimensional problem, you have a very good idea. The surrogate model is a very good representation of the true model. But if you use different approaches trying to represent the trying to construct this to create those points, and some approach use a linear approach, maybe it's the between points uncertainty is very, very small. But if you use like a higher order, like quadratic, then you have maybe a lot more uncertainty between the sample. So probably so that's the idea. Okay, so there's a lot of details. Okay, so how do you create the samples, and how do you validate the how do you validate the surrogate model? Because the surrogate model is a very dangerous tool. You have to be very careful. You have to validate the surrogate model, and so you have to use some kind of error measure. And there are all kinds of different error measures. I don't have time to go through. And so one way to do the validation is so-called k-fold cross-validation. How do you do it? Suppose I use 200 samples to construct the surrogate model. And I divide the 200 sample into 10 groups. Okay, so each group has like 20 points. And then how do I do the cross-validation? We throw out one group and then use the 9 other groups to do the construction of the surrogate model. And then you get a difference between the response surface using 200 points versus 180 points. And you get the difference, you do it 10 times. If the difference is within your tolerance, then say, okay, 200 points is enough. If it's not, then you can create more points. And then you go through the same process and until those kind of k-cross validation give you the answer you are happy with. Okay. So this is just example using Rosenbrock. Suppose like right now, you use 10,000 points to create the response surface. You are very happy, okay, because this is a very true description of the Rosenbrock function. But if you use the surrogate model, just I use only 100 samples, and you can see using this mass is the surrogate model approach. This is very, very bad. Suppose like right now, if I use all other different kind of function types with the surrogate model, use the quadratic regression. I only use 100 sample points, and this is very, very good representation of the true response surface. And of course, you talk about you're cheating here, okay? This is the quadratic function. So if you use quadratic function in theory, actually you only need like 1, 2, 3. You use three samples. You're able to construct a very exact surrogate model for this Rosenbrock function. Probably I'm jumping too fast, but if you have time to play with my software, I think probably you will gain more understanding of this. Okay, so I just want to say, okay, surrogate model is a very dangerous kind of tool because you're trying to use a statistical model to represent a dynamic model, and you want to make sure the surrogate model is reasonable. Okay, so you have to take a lot of those kind of caution when you use surrogate model. And so then you have optimization and model calibration. It's, sometimes people say it's parameter optimization is model calibration. And I think probably I have to go very fast. Okay, so the idea is this. Okay, if you have real system, you use the model, and the model, if you use some kind of a priori parameters, and it's not good representation of the real process, and then you tune the model parameters through some kind of optimization algorithm. So this is, you get a better fitting. Okay, that's the idea. And so there are different ways. You have those so-called deterministic optimization methods, trying to use some kind of algorithm to find a single set of optimal parameters. And there are different methods to do that. And then you have stochastic optimization. That means you assume the model parameters, you don't have a unique set of optimal. You're using so-called Bayesian, like the MCMC kind of approach. You give you a distribution, a posterior distribution is the solution. So right now, let me just go directly to some of the examples I want to. I don't think I have time. This is SCE actually is the algorithm I created many years ago, and it's still very, very popular in hydrology community. And so I don't have time to go through how this thing works. Actually, I have this.
10 minutes more, so you don't need to be too fast.
All right. 10 minutes more. But anyway, SCE is a algorithm which is a combination of genetic algorithm and the local search. Okay, and so it's much more efficient than genetic algorithm, but it retains the global search property of the genetic algorithm. And probably I think I don't think it's it's easy to just say in 1 minute how it works exactly. But anyway, if you, this is an illustration of how this thing works. And we have another algorithm actually is called adaptive surrogate modeling based approach. And this approach it works like this. Okay, suppose this is the true model, okay? The true model, and then you sample in space, okay? You sample on this dimension, and then use a statistical model to fit in here, okay? You can see like this is a surrogate model, okay, of this true model. And once you have this, okay, you have this thing here, okay, you evaluate, then you find like right now there is the promise area, that means the lowest point area. You can put more additional points, additional sample. And then you do a larger surrogate model. And you can see like the second surrogate model is getting closer to the true model. So that's the idea of this so-called the adaptive surrogate modeling based approach. And the reason I mention this is because we have been using this to optimize the wolf model. And so right now we just say, okay, we have covered this. Okay, right now let me go to some kind of case study. Okay, so I want to skip the non-surface model. Okay, I want to go directly to this wolf model. So the non-surface model, maybe I just jump very quickly. This is a model. Actually, is the right now the community land model actually is based on the common land model. It's developed by my colleague from Beijing Normal University, Qingyun. The current community land model actually has basically the same kind of physical structure, except some kind of details are different. And so this is the study basin. Then for the common land model, we talk about many parameters. Okay, we talk about 40 of those parameters, which you can tune. And so I worked with Qingyun, and we found the uncertainty range, and then we are trying to see which parameters are important. So we evaluate against we using those different screening methods I just mentioned before, and then we also used a quantitative method to quantify the importance. Okay, so this is a screening output. Okay, suppose you're using different sampling approach, or you use a different number of samples, and so the longer the leader, that means the more sensitive the parameter is. And you can see this is 1 to 40. So that means like this parameter is very important. Like some of the parameters are not important. If there is no lead, that means that parameter is not important. And you can see like doesn't matter which sampling approach you use, or how many like 200 or 400 or 1,000, seems like give you very much the same kind of output. And so this is another way, because we look at the sensible heat, we look at latent heat, we look at the upward downward radiation. So the dark shade means the parameter is important, and then the light shade, that means it's not important. So some methods doesn't work too well, like the local method, because when we talk of sensitive analysis, a lot of people probably have worked with some form of sensitive analysis approach, is so-called like just use some kind of perturbation. Okay, so you perturb one factor at a time. Okay, you perturb. You start with some kind of initial point. You perturb this way and probe that way, and then get the gradient. That's the local sensitivity measure. And that measure actually it's not reliable, shown here. Okay, you can see that if you use local sensitivity analysis, it's not reliable. Give you like type 1 error or type 2 error. That means the important one you say is unimportant, or the unimportant one you say is important. So the local method is not a good sensitivity method. So that's the take-home message. And then there is another approach, is a theta test. Actually, theta test also doesn't work too well when the number of sensitive parameters is very high, or relatively high. You talk about more than 2 or 3. That's because the algorithm using genetic algorithm, a fixed iteration of genetic algorithm to find the optimal set of important parameters. because we use only 500 iterations for the genetic algorithm, when the dimensionality is, the number of sensitive parameters is higher, then it doesn't converge. So data test doesn't work. But sum of tree, mass, Morris method, very, very consistent. Okay, so this is for 3 output we are looking at. And then if you look at all other 3 output in soil moisture, soil temperature, and lead radiation, you can see local still not working. Okay. Other methods are very, very consistent. Okay. Also, one of the striking things is this: even though we started with 40 parameters, the input parameters are not that many. Okay. For soil moisture, only 2 parameters, or maybe you look at this. Okay. 2 plus or other 2 have some kind of influence on the model output, but in this one has 3. Okay. So that means don't tune 40 parameters. Okay. If you tune 40 parameters, you're not going to gain much. And so this is an example of using quantitative methods. You can not only identify the important parameters, like this, each slice of those pi represent different parameters. Like this P6, parameter number 6. Okay, so it contributes like 33%, P36, 32%, 32.9%, and then other parameters, you have small contribution. Okay, so if you look at those 2 here, okay, soil temperature and soil moisture, you can see like soil temperature has only 2 important parameters, and soil temperature has 3. Okay, soil moisture has 2, and soil temperature actually is pretty much consistent with these quantitative methods. Okay. The quantitative method usually requires a lot more, and you just saw that we use 2,000 model experiment to get the quantitative output. So here I just want to show you, okay, using the qualitative method, which only require like 200 to 400 samples, give you very robust output. So this is just to give you some kind of confidence using those qualitative methods. And we also did some kind of optimization. And right now, I just want to give you a take-home message. Yeah, if you're trying to calibrate individually to soil moisture or soil temperature, sometimes you get this is the optimal parameters. Okay, you're talking about the converged optimal, and the optimal if you only optimize on soil moisture, it requires to be like 0.8, and if you calibrate to soil temperature, it requires to be like 0.4 or something. And this is for the same parameter, the P3, and this is P6. This one's close to be 1, and this one close to be 0.1. So that means if you want to calibrate to a single output of your model, and sometimes the optimal parameters, they don't agree. So you have to use a multiple objective function. And this is the output of a multiple objective function. When we're trying to use a multiple objective optimization, and we can improve pretty much everything except the temperature, okay, the soil temperature. So you sacrifice soil temperature a little bit, but soil temperature is already very good, okay, and then you can improve everything else, any other observation you are interested. And this is the comparison of using surrogate model, and this is just SCE, the method which is not more expensive. Here we set a maximum is 100, and you can see like 100 compared to 400 here. So that means the surrogate model has a efficiency advantage here. And so we just have a quick summary, and I don't want to read through, but you're going to have this copy of this slide. And then we are trying to show you quickly the Wolf model optimization. Wolf model, probably you know more than I do, because I'm a hydrologist. I have this excuse, I'm not a climate model or the weather model. But we use our methods on this Wolf model. Okay, Wolf model have all those different processes. And Wolf model, it's not just, of course, it's just not about the model parameter optimization, but also about the compilation of different schemes. This is 3.3, actually. This is the old version of the Wolf. But you look at it, for each of those processes, macrophysics, you have 14 different choices, okay? Non-wave radiation, short wave radiation, and etc. You have more than 1 million combinations, okay, in theory. And so there is a problem, which physical processes, that means which of those processes are most important or most sensitive in terms of to the meteorological variable of our interest, for instance, precipitation or temperature. And this is a important question, for people. You have to answer. And then, what combinations? Okay, that means how do you choose those different combinations give you the best Wolf model configuration you can use for your particular application. And we have done some research. Okay, I'm not going to talk about. We have done some research on create a physically based ensemble forecast for the Wolf, but here I'm going to talk about giving a particular compilation of physical schemes, and how do we find the optimal parameters or the sensitive parameters, and how do we optimize them? Okay, so this is the thing I'm going to talk about here. This is the domain. Okay, we are actually trying to improve the 5-day forecast of the greater Beijing area. So this is a Beijing area. Okay, so we have a 2-level nested grid setup. So the outer domain, you talk about 27 kilometer resolution, and the inner domain is like 9 kilometer resolution. And so we're trying to pick some 5-day forecast to calibrate the parameters. Okay, so the 3 year we work with, 2008 to 2010, from the summer period, because in Beijing and in most of China, we have big seasonal variation of precipitation. Most of precipitation occur during these 3 months, the June, July, and August months, about 70% in China. And so we pick some big events trying to tune the model parameters. Okay. So these are the parameters we identified from different schemes in the Wolf model. Some of the model parameters are from surface layer. 5 of them came from cumulus cloud, and 4 of them came from macrophysics. 2 of them came from short wave, 1 from long wave, 4 from land surface, and 5 from the boundary layer. When we identify, we're trying to really, see, okay, if it has to do with the surface temperature and the precipitation. And we actually had a lot of communication with some experts, including the model developer or some other advanced modelers, and to identify the reasonable range. I want to say, those list of 23 parameters are definitely not inclusive of all the tunable parameters, and this is just a illustration of this methodology, and in reality probably have a lot more than 23. And so this is the summary of the setup. You have 2 levels, and then you have 9 5-day forecast. We use the ANSYS real analysis to initiate to set the lateral boundary condition. And so each of those 5-day forecasts actually take about 4.5 CPU hours to make just a 1 5-day forecast. And you talk about 9 5-day forecast, you talk about 180 CPU hours. So that means, to do 1 model experiment is 180 CPU hours. So it's not impossible nowadays, but it's still a lot of computer hours. And so we try also use some kind of data to help us to understand, the sensitivity, okay, including the conventional data and also some of those, the cloud fraction, the total precipitable water, boundary layer height, and then upward non-wave radiation at the top of the atmosphere. So we use the Morris method to do the sensitivity, and then we use the objective function is the mean absolute error of the simulated output was the observation. And so for Morris method, we talk about 240 model experiment. So you talk about 43,000 CPU hours for us to complete the sensitivity analysis. So here is the Morris output, and so this is the first day. Just look at the first day forecast, first 24 hours, second 24 hours, third, fourth, and fifth. And this is look at all 5 days together. And so the number here are index for the parameters. Okay, so like 21 and 4. That means those 2 parameters are the most sensitive. The 5 and 16 for the first day, and then 21 and 12 and 16 and 4 and 5 as for the second day, and etc. And then this for 5 days combined, 12 5 and 21 and 16 and 3 and 2. Basically, if you look at here, right now it's very hard for you to read, but those 6 parameters tend to stand out as the 6 most sensitive parameters. Doesn't matter which day you look at, and also we're trying to look at using the convective storm or the non-convective storm or the mixed storm, and the results is not too sensitive to those things. Maybe the order, for one parameter is ranked number 1 on the first day, or other one number 1 on the second day, etc. But the 6 most sensitive parameters are pretty consistent. And so this is another way to plot this. Okay, we normalize the sensitivity index. One is this pink color, and then this is the cyan color. So the sensitive parameters are pretty much consistent. For individual, this is like July events, this is August event, this is the June event, this is the total event. There's a lot of consistency, but for some individual events, there is some kind of discrepancy. Okay, but overall, I think there's a lot of consistency in terms of sensitive parameters. And here is another way to look at confirm the sensitivity. We talk about using the maximal parameter or the minimal parameters. These are the 23 parameters. Okay, so this is the 45-day difference, precipitation difference. So the sensitive parameter, you can see it's a big difference. Okay, here is plus 2 millimeters. This is minus 2 millimeters. But if you look at some of the parameters, it has absolutely nothing to do with precipitation. Okay, so those 2 parameters are not sensitive at all. Other parameters are not as sensitive as those 7 parameters, so those 8 parameters. Okay. So we are. This is also we look at some other variables. Okay, so these are the precipitation I just presented, and then we also look at this is the precipitation. Okay, and then we look at the surface temperature, and we look at the surface pressure, and then look at the relative humidity, and the wind speed, the downward non-wave radiation, and the downward short-wave radiation, etc. So this is also look at the cloud fraction, which parameters are sensitive, and then the outgoing non-wave radiation, and then the total precipitated water, and then the planetary boundary layer height. And this is a summary of those things here. Okay, you can see like the 7 surface variable and then the 4 atmospheric variable. So the dark color here means it's sensitive, and then this light color not sensitive. You can see there's a lot of consistency. It doesn't matter which variable you look at. Some of the parameters are important all the way through, but the other parameters are only related to those processes. Like for instance, like these parameters are only sensitive to the downward non-wave radiation. And this, are for those 4 variables, and like this one only like planetary boundary layer height, are only these parameters are only sensitive to the planetary boundary layer height, and etc. So those work actually set up us for the optimization. Those things actually identify the important parameters. Once we identify the important parameters, we only optimize on those parameters. We don't optimize on everything. We don't optimize on all 23. And so this is the optimization setup. Okay, we optimize on the 8 parameters. Remember, 8 parameters are very sensitive to the precipitation. So we optimize on the 8 parameters, and we use the MAE as an objective function. And then, so we did 3 sets of optimization. One set of optimization one is optimize the precipitation only, or other is optimize the surface temperature, and then also optimization one optimize both precipitation and surface air temperature. And this is the convergence process. Okay, so we talk about, after about 200 model runs, we find the optimal for when we only optimize the precipitation. When trying to optimize the surface air temperature, take us less than 150 model experiment. And when we try to optimize both, actually take us about 230 something. Okay, it converges. So this is just give you a sense of the effect of optimization. So this is the observation we are looking at. This is the 45-day average of the precipitation. And if you use default, you can see there's the obvious overestimation if you use default parameters, okay. So when you're trying to optimize the precipitation only, actually you have reduced the overestimation. And if you optimize both temperature and surface temperature, you also reduce from here. But here actually it's kind of deceiving. It's very hard to see. Let me just, this is the temperature, it's harder to see. But let me just show another plot. Okay, so this is, say, okay, so right now, you have these 9 different events, okay. The 2008 June events, 2008 July events, and etc. You can see, like, right now, this is the average, or observed average, the green, the blue one, okay. The default, you can see every time they overestimate, okay. And then when we did the optimization, it's sometimes it doesn't improve, but most of the time it does improve. This is look at the mean absolute temperature, the same thing, overestimation in most cases, and then the optimized actually has a better, closer to the to the observation. And here probably just shows you more clearly. This is the like the white one here actually is the default parameters. This is the MAE. We're talking about the mean absolute, normalized mean absolute error. And you can see like the dark one is the optimized error measure. You can see for this event improved 19%, this event 12%, this event 18%. And overall, it's like 17% okay? And occasionally you have a not improve every event. Like this event, you degrade by like 5%. And this is trying to optimize the temperature only. Also, it has big improvement most cases, but occasionally you have degradation for a particular event. Overall, you talk about 18% improvement. And then this is trying to optimize both, and you can see also improvement, except in 2 events it doesn't improve. And so this is the optimized parameters, and just tells you this is the default parameters, and sometimes it just push it up, sometimes it push it down, depending on the objective function. Okay, and there is a lot of consistency in some cases. Okay, so people say, okay, you are feeding, the observation. Of course, you are going to improve, but we also use independent validation data. So the red box actually are the out of sample data. We're trying to validate the optimization output, optimization results, and so this we choose 6 events to validate. Okay. So again, this shows the average. The average sometimes is kind of deceiving. Okay, and let me just go directly to here. Okay, you can see the validation. You have improvement all around. Actually, validation actually is better than the calibration itself. So we have when we trying to using the optimized parameters on those validation data, it improves every time. And the overall improvement, you talk about like 21%, 18% to 21%. So that means the optimized parameters, if you use those instead of the default, do give you better predictions. Okay, so this is a summary of the optimization. We use 240 runs to get the sensitivity, and then we use these are the sensitive parameters. And then when we try to use do the optimization, we are able to achieve improvement at like 14 to 17%. And then when we do the validation, we are able to maintain those 18 to 21% improvement. Overall summary. Okay, so right now, I just wait too long. I get 10 minutes over. So we have expanded the UQ concept. We have introduced some of those techniques, and then we did a case study with the common N model and the wolf model. And so the take-home message, okay, UQ is an essential tool for improving model performance and automatic optimization of complex geophysical model like the common N model and the wolf model is possible. So this is the take-home message. And I don't know, I have to entertain questions. Maybe I do.
We should, yeah.
Okay. I know I jumped too fast in some of the details, but here I just trying to give you an idea we can use a fully automatic kind of approach, trying to optimize the parameters of those complex models, like the Wolf model. Right now, we are pursuing the same approach for climate model. Okay, climate model, you talk about a different category. Even like weather model, 40,000 CPU hours is nothing. When you talk about climate model. But anyway, the kind of approach we present, make it feasible, to take those kind of approach. All right. Okay.
Thank you for your presentation. For developing countries where the computational resource is limited, do you think running a very high resolution model would be a better choice rather than uncertainty quantification for the case of precipitation, or no? Probably I'm not in the best position to answer this question. Here we're just trying to demonstrate, okay, there is one area which has not been worked on or have been not focused on too much, the prompt estimation aspect. And to do that, this is a viable kind of thing you can do. But in terms of choice between uncertainty quantification and high resolution, I don't know. It's hard. It's hard to because they're trying to address different issues. Okay, and indeed, I think nowadays the computational resources, I think there's a lot of advance in terms of computational advance, and hopefully, you can do both.
Yeah, I mean, all I would say is that when you look at the gap between a model and the data, do you want more models that are off, or would you try to put more effort into trying to reduce that model data gap? And we're probably still, I would say most scientists are more enthusiastic about reducing model data gap and are less, let's say, less interested toward exploring parameter space. But it will depend on what's your priorities. Like if you're worried about extreme events or climate change or some big something that it may be more worthwhile to take a different approach.
Because it has been discussed that, for example, for the case of convection precipitation, the resolution more than 4 kilometers is not very compared to the other resolution. For example, let's say 15 kilometers or 27 kilometers, there is not any significant change. I'm not sure whether it's true or not, but for the case of convective precipitation, I mean,
I'm a hydrologist. Like hydrology, also we have this argument about distributed model and lumped model, and so a lot of people feel there is an advantage, there is an inherent advantage of distributed model because it gives you better description of the representation of the heterogeneity. But in reality, the issue is like, do you have enough data to support your high resolution? That's something you have to consider. Sometimes just go high resolution doesn't necessarily give you better output. I remember when I was working in National Weather Service, after 911, people in California, they feel, okay, this the topography, basically, you need high resolution to present the topography in the West Coast. So they go from the, I think, that time I think the operational resolution was like 30 kilometer, about 30 kilometer, and then for California it goes to 10, and then they saw there is a degradation in the skill score. Somehow, you don't improve. You actually you decrease the predictive score, and so there are many issues in there. One is like your physics actually will not develop at that resolution. That's one of the issues. And another issue is that when you go high resolution, you have to have the right data to configure your model, and sometimes that doesn't happen. When people just when they go high resolution, they didn't really do the other necessary thing to, to make sure it's suitable for the high resolution. Yeah.
Thank you. When we say optimization or calibration, is there any difference between them, or is it the same?
It's a different terminology people use. Like model calibration tend to mean optimization of model parameters. Okay, and I don't know why there's those kind of different terminology, but somehow we use interchangeably sometimes. Parameter optimization, model calibration.
So I used to resist calibration. I was like, but I guess the statisticians use the word calibration to mean to estimate, which whenever you involve a statistician, they do probability distribution. So they mean to generate, and I think in the engineering community, optimization usually means to find the minimum of your objective function, and that means the mode of your distribution, or the maximum likelihood estimate, which means usually you're trying to find one single model version that will give you the best skill and without uncertainty. So I don't know, when you do optimization, are you thinking about uncertainty?
Of course, sometimes you make an assumption. A lot of uncertainty can be attributed to the value of the parameter estimates, and this, of course, is not necessarily true. But when you take that approach, you make the implicit assumption that okay, all the errors can be attributed to the specification of the model parameters, and people, of course, sometimes taking measures like using the right so-called objective function. There's your objective function is like the MAE I showed here, or the root mean square error. But the root mean square error it actually works when the error, the residual, have this Gaussian distribution. But if it's not Gaussian, then your estimate is biased. But sometimes we just for mathematical tractability, we didn't pay attention to the distribution of the residuals. And so our estimates will give us the better metric, the objective function. But the estimate is biased. It's not the true estimate. Yeah. And so that thing will show up, when you trying to use an out of data sample. That means like for the feeding data, you have better output, you have better results. But if you go to in the data, independent data, then maybe that's when the problem will show up.
I think we should break here. What I understand next is 2 more lectures. We have there's a dinner, right, tonight at 7 on the terrace, and I think that's and then tomorrow morning at 9.
All right. Yeah. Just again, I mentioned this software package. I think you're going to everybody get a copy of the presentation, right?
Yeah, that's right.
Okay. Okay. So also, on the list of participants, you got my contact information as well. So welcome you to send me email, and any questions, we can discuss by email.
Hey, Charles, right. One last thing. For those of you that may want to look at R or want to do a little more with that, or want to try to catch up, Chris and I were willing to meet in the computer lab at lunchtime tomorrow for anyone that just wanted a little one-on-one trade just to get up to speed with R. And so it won't be exactly at lunch, it'll be 15 minutes later so we can grab something, but then we'll be happy to meet anyone who wants to go down there for that.
Excellent. Thank you.
By the way, for the reception, your family members, if they are here, of course, also are invited. So.
Okay.
All right. Thank you. All right.